So let's just start the class. I'm waiting for others to join. I hope my screen is visible to everyone. Can any one of you confirm it? Okay. Shall we start? Say yes, at least. Okay. Let's just start.
No, ma'am, the screen is not yet visible.
Okay, my screen is not visible to you.
No, ma'am.
Okay, it's the problem with other one also? With other students?
Yes, ma'am.
Okay, let me see. Let me see what is the problem. My screen is not visible. I think some problem is coming. I will see. I will see. Is it visible now?
Yes, ma'am.
Okay,
Yes,
thank
ma'am.
you. Thank you. Thank you, everyone. Okay, now let's just start the class. This is the first question. The total angular momentum J of the ground state of oxygen nucleus is. You need to find out the total angular momentum of oxygen nuclei. This came in GATE 2022. Now, to solve this question, what you need to do? You need to fill these sublevels. But before filling these sublevels, we should know the background of it, like how these sublevels are coming, what is the physics behind it. Okay, so this is oxygen nuclei or any nuclei you can say. It contains neutron and protons, right? They are collectively called nucleons. Okay, this nucleon has orbital angular momentum and spin angular momentum, right? So what is total angular momentum? Total angular momentum, you know, it is L plus S to, oh sorry, it is L plus minus S to L plus S, right? Okay. So this, suppose this oxygen nuclei has orbital angular momentum of L and spin angular momentum of S. This proton and neutron are fermions. So you know the fermions are half spin integral particle. Okay. Sorry. Half integral spin particle, right? This means the vector addition of L and S will give you J value. Okay. and the J value is restricted to L minus S to L plus S. That means L minus 1 by 2 to L plus 1 by 2. This L minus 1 by 2 when L is anti-parallel to when this L is anti-parallel to S. Okay? When this L is anti-parallel to S, then J will take L minus 1 by 2 value, and when L is parallel to S, then J value will be L plus 1 by 2. Right? Now take a case here. So suppose here, take a case. L is equals to 0. L is equals to 0 and S is equals to 1 by 2. That means J is equals to L plus S, 0 plus 1 by 2 is equals to 1 by 2. That means you can see here, as you can see here, this is 1s 1 by 2. Why s? Because L value is 0, and you know it very well. When L is 0, then it is s. When L is equals to 1, it is p. When L is equals to 2, it is d. Okay, and J value is given here. This is 1 by 2. Now, how many neutron or proton this 1s 1 by 2 sublevel can house? That will be given by 2j plus 1. Okay, that means if suppose j value is 1 by 2, so it can house how many neutron or proton? 2 neutron or proton. Got it? This I have explained about this state. This state. This is. If you take uh, this case, L is 1 and S is equals to 1 by 2. So there you will see L minus S is equals to 1 minus 1 by 2 is equals to 1 by 2. There is one state, that is 1p 1 by 2, and there will be one more sublevel, that is L plus S. 1 plus 1 by 2 is equal to 3 by 2. That means 1p 3 by 2. So these two sublevels because of this. Okay, so in a similar way, when L is equals to 2, so there you will see there will be different state. So that is why these sublevels are there. And you know how many neutron or proton these sublevels can accommodate. So if it is 3 by 2, J is 3 by 2, that means it can accommodate 2J plus 1. That means how much? 4 nucleon. Nucleon means 4 neutron or proton. They will be filled differently. Now here you can see the oxygen has how many proton? 8. And what is the number of neutrons? 17 minus 8 is equals to 9. So can any one of you tell me which one will provide the total angular momentum? Because proton is even and neutron is 9. So neutron will play the deciding role because this proton will couples to give J is equals to 0 because they are even. So they will couple to give J is equals to 0 like this way. 1s 1 by 2 will fill 2, 1p 3 by 2 will fill 4, and 1p 1 by 2 we can fill 2. That means they are all filled. The only deciding factor will be neutron. So let's just fill neutron. 1s 1 by 2 will 2 neutron will be filled in this sublevel, and 1p 3 by 2 means 4 neutron, and 1p 1 by 2 means 2 neutron, and 1d 5 by 2 can accommodate 6, but there it is only 1. So this is the total angular momentum of oxygen nucleus. That means the answer is 5 by 2. So see, in this question only angular momentum is asked. See, angular momentum is asked. Suppose if they asked you to find out the parity also, so how would you have performed if parity was also required in this question? Because right, currently we are asked only angular momentum. So if question such question is coming in the examination, like you have to find out the angular momentum and parity, then parity is, it's very simple. Like last class we have done the beta decay. In it I told you like parity is minus 1 raised to the power L. So you just have to find out that the last neutron went to this state, this sub level. So here D. So D means L is equals to 2. Okay. So parity will be minus 1 raised to the power 2. So it is positive. So that means it will be 5 by 2 positive. So parity was not asked in the question, but I just told you, like if suppose angular momentum and parity both are coming in the examination, means you are asked to find out the angular momentum and parity of any nuclei. So this is the way you should do this question. I hope this is clear to everyone so that we can proceed for the next question. And I
Ma'am,
want, yes,
ma'am, I have a question. Can we use the Hund's rule?
Hund's rule, Hund's rule.
This rule also calculate the ground state of the Trump symbol,
Okay.
and we have used here the shell model from the
Hmm.
nuclear fusion.
Nuclear, huh.
Uh, that is the basically ground state spin pairing.
Hmm,
Okay,
hmm, hmm.
can we use the Hund's rule? Because
Uh,
Hund's also gives the ground state Trump symbol.
Okay, but actually, see, Hund's rule, talking about Hund's rule, so I have not prepared for Hund's rule. If yes, I can take your query and will explain you in the next class.
Okay, ma'am. Okay.
Okay, huh? Thank you for asking the question. Right. So I want the next question for you guys. I have prepared this question. I mean, this also came in the gate examination, but I want you to at least do this question. 1 or 2 minute time I'll give you. So this question is the nuclear spin. See, here it is asked, find out the nuclear spin and parity of calcium in its ground state. So you just answer is clear, like answer is A, but I want you to at least try this question. I'll give you 1 minute time. Everyone, please do this question. I can give you this figure is 20 calcium 40. I'll give you this figure so that it will be easy for you to fill that.
Ma'am, 0 plus.
Yes, correct. Because you can see here that if you start filling the neutron and proton, so here you can see neutron is also 20 and proton, the number of protons are also 20. So both are even, right? And I told you if this is even, that means total angular momentum will be 0. Now you need to find out the parity also. So just start filling in this. 3 by 2, 1p, 1 by 2. What is next? 1d 5 by 2, 2s 1 by 2. 1d 5 by 2, 2s 1 by 2, and 3d 1 by 2. So last will go in this subshell. So here d is 2, right? L is equals to 2 for d. So minus 1, 2 is equals to 1. So that means the answer is this one, 0 positive. So it was a very straightforward question. All these questions came in gate examination for 1 marks. So these questions are like you can score more marks in such questions because they are very straightforward. Here we are also knowing the background of it, but in examination you just need to start filling all this shell, everything. This is the third question. This third question is from particle physics. This is a very interesting question. I mean, it's like you just need to spend only one, like it's the question, like it's a 2 second question. I mean, it's a really very simple question, but we will do it in a traditional way because to know everything, like otherwise this is a very simple question. So we'll start. Here I'll read the question. A particle X is produced in the process pion positive, proton, cation, and this X. We don't know what is this particle, and that we need to find out. So this process is going via strong interaction. You know, all the particles that are involved in this process are hadrons, and hadrons undergo strong interaction, and leptons undergoes weak interaction. Leptons do not undergo strong interaction. So if the quark content of K positive, it is given to us US bar. Okay, the quark content of K positive is given to us, and we need to find out the quark content of this X. As the question says, first thing we need to do is to identify the particle. But before that, again we'll go for the background of it. This is hadron. Hadrons are divided into two classes. One is baryon, other one is mesons. Baryons are fermions. Okay, spin half particle, and mesons are bosons, spin integral particle. These baryons are further divided into baryon and baryon resonance. For baryon resonance, we have 1 by 2 positive. That means angular momentum is 1 by 2 and parity is positive. And for baryon resonance, we have angular momentum 3 by 2 and parity positive. Now there is one more class, that is mesons. Mesons are further divided into pseudoscalar mesons and vector mesons. These pseudoscalar mesons have angular momentum 0 with a parity negative, and these vector mesons have angular momentum 1 with a parity negative. Okay, these are the hadrons. Then in baryons, you can see here that this baryons contains how many? 1, 2, 3, 4, 5, 6, 7, 8, 8 elementary particles. And this pseudoscalar mesons again contain 1, 2, 3, 4, 5, 6, 7, 8, 8 particles. Now, you need to find out this reaction is proceeding via strong interaction, and there are certain quantities which need to be conserved when such reaction is going on. Certain quantities. If I look into this equation, so I can easily say that here charge is plus 1, right? Proton charge is also plus 1. So here it is plus 1. So this X particle should also have charge plus 1, right? So the charge should be conserved on both the side. So we will look into these quantities one by one and try to conserve them, like matching them. If left hand side is equals to this number, then right hand side should also match the same number. To conserve these quantities, then only we will figure it out which particle is this. So here it is. Now if you see charge, very straightforward. No, nothing we need to see. This is spin. Now you can go back and look into the table, the spin of pi positive. Sorry, it is yeah, it is spin. So the spin of pi positive is 0. It is fundamental, right? And for proton, it is 1 by 2, since we have already seen that protons comes under baryons and baryons are fermions. So this spin is obviously half integral, and this the spin of cation is 0, then technically the spin of unknown x particle should be 1 by 2, because left hand side quantity should be equal to right hand side. Okay, they should be conserved. Now again, this is the baryon number. So all those particles which comes under baryon have baryon number 1, and all those particles which are not baryon have 0 baryon number. So pion is a meson, so it will have 0 baryon number. Proton is a baryon, so it will have plus 1. Cation is a meson, again, so it will have 0 baryon number. And this unknown particle is, so this unknown particle should have baryon number 1, because baryon number should be conserved. So by this, we got the idea that this particle belongs here in this table. So now we'll look up further quantity to identify it. This is isospin. Isospin. So isospin, what is the meaning of this isospin? Okay. So we'll look what is isospin. Suppose we have a system like such an environment in which we have placed proton and neutron both. Where is my, okay, proton and neutron are placed in such an environment where electromagnetic field is not present. So how you will distinguish between proton and neutron? Because proton and neutron almost have same mass, right? So this nucleons like proton and neutron or any other multiplet can be differentiated by this quantity which is known as isospin. This proton and neutron, the multiplet number of this will be 2. So suppose if I have asked you to find out the isospin of this nucleon, so then how you will do? So you will apply this formula. Okay, sorry, from my end, this is thing. So 2 is equals to 2I plus 1. Why this 2 came? Because there are 2 in number. Okay, 2I is equals to 1, I is equals to 1 by 2. And there is one more quantity, that is iz. Here it is I3 written. So iz basically, it is the I value along z direction. So the I value along z direction is called iz, and the iz value varies from minus I to I, right? Now I'll show you how this value came here. So this is wrong. I mean this I'll show you. First is pion, right? Pion are triplet. So how many of them are there? 3. 3, 2I plus 1 is how much? 2I is equals to 2. I is equals to 1, right? So Iz will vary from minus 1 to 1. That means Iz will have 1, 0, 1. So that means pion will have value. I will remain the same for everyone. Only thing will change this Iz value. So this is 1, 1, this is 1, 0, and this will 1 minus 1. So here the value will be 1. Okay, 0, it is wrong. And for pion, what will be the sorry, for proton, what will be the I value? So I told you here it is I value came 1 by 2. So it will be 1 by 2, correct. And for cation, it will be, cation has how many multiplet? Cation, where is cation? So cation has 2. So that is 1 by 2. The multiplet number is 2 for cation. 2. That means 2I plus 1 is equals to, I is equals to 1 by 2, right? And cation will and Iz will be 1 by 2 minus 1 by 2. right? So K positive will have value 1 by 2 1 by 2, and K negative will have value 1 by 2 minus 1 by 2. That means I will remain the same, only Iz value will vary. So here it will be 1 by, so here it will be 1 by 2, and this will become 1. Sorry, this is wrong here, this I value is wrong, so what I am doing is correct. This is 1 by 2 and this is 1, right? Now Iz value. So Iz value I already found out. So it, for pion it will be plus 1. For pion it will be plus 1, and for proton it will be 1 by 2, and for cation it will be 1 by 2, and for this again it will be plus 1 to balance both side, right? Any doubt here? Now the next thing is strangeness. Strangeness basically means there are certain, there are certain particles whose formation are governed by strong interaction, but they decay via weak interaction, so they are known as strange particle. If you look here for pion, so the pion here has zero strangeness. And how this strangeness is coming, you don't need to learn it by heart. If you know the formula of Gell-Mann-Nishida formula, so the Gell-Mann-Nishida formula is Q is equals to I3 plus B plus S by 2. This B is baryon number, and this I is, sorry, this is IZ, I3 or IZ, whatever you can write. It's up to you. Okay. And this is Q is charge. So if you suppose you need to find out the baryon number, oh, sorry, the strangeness of proton, I'll find out the strangeness of proton.
Ma'am,
Yes.
hypercharge is only B plus S, or the
Yes.
other charm. This has to be added, ma'am?
Hypercharge is B plus S. Okay, so if I'm finding the strangeness of proton, proton has charge 1, I3 is 1 by 2, as we have calculated in the next previously, and baryon number is 1 plus S by 2, right? 1 minus 1 by 2 is how much? 1 by 2, right? 1 by 1 by 1 minus 1 by 2 will be 1 by 2, and this 2 will go here. Okay, this is S plus 1, so this is 1 and this is 1, so 1 1 will cancel and it will be 0. So see, the strangeness of proton is 0. So similarly you can find out the strangeness of any particle if you know. So if you are very good in memorizing things, you can memorize this whole table, but if suppose someone who is not good at it memorizing things, so you can apply this formula. I mean, this formula is there, Q is equals to I3 plus B plus S by 2. I3 is just the Z component of isospin, Q is charge, and B is baryon number. From that, spin strangeness will come. Okay. So now you can see here. Here you can see strangeness is 0 for pions and it is 0 for proton also. But it is plus 1 for cions positive. Now, so technically, not technically, so it should also have, the unknown particle should have strangeness minus 1, so that plus 1 and minus 1 will give 0, because left hand side the strangeness is 0. Now just we can identify which particle is this from this list. This is charge is plus 1, I is plus, I3 is plus 1, baryon number is 1, strangeness is minus 1, hypercharge is 0 because B plus S hypercharge, that means it is this particle. And for that, quark content is UUS. You know it. One more thing I want to add here, that baryons are made up of, you can see baryons here, they are made up of three quarks. But on the other hand, mesons are made up of one quark and one anti quark. Okay, now you can see this one is matching with it. So the answer is this one. You can solve this
Ma'am,
question. Yeah,
how do I find that sigma plus has the quark content
UUD.
UUS?
Yeah, yeah, very nice question. You can go here. This is the table of quark content. This table. So by this table, so proton has plus 1, right? Proton does not have any strangeness. So that means these will not come into the picture. So U up and down, and these quarks are like these two quarks are first generation quark, these two are second generation, and these two are third generation. Okay, so proton and neutron does not have strangeness content. So strangeness will not come into the picture, only up and down. So now you can see proton has charge 1. Here you can see u this one. Charge for u is 2 by 3. There is one more u, and there is d 1 by 3. So that means 4 minus 1 is equals to 3. So charge is e. And baryon number UUD, for UUD baryon number is 1 by 3 plus 1 by 3 plus 1 by 3 is equals to 1. So similarly, you have this unknown element that we just found out. It is this one, this particle. So for that, we found out that it should be UUS. Why? Because now you can see here, if you add 2 by 3, 2 by 3 with S is minus 1 by 3, you will get a charge plus 1. And one more thing is, this table is, uh, so from this table you can see this strangeness is minus 1 for it, and we have found out that strangeness is minus 1. So S will come. If suppose instead of in strangeness coming minus 1, it would have come like plus 1. So that time you will take S is equals to S bar, because this is anti-quark of S. Now you can do this quark content table by yourself by looking into charge or other values. This is like you can take it as a homework. I mean, for one I have done for neutron. I mean, why it is U D D, because U has charge 2 by 3 and D 1 by 3 minus 1 by 3. So it is 0. Charge is 0 and neutron has charge 0, and there is no strangeness involved in this. And now you can see if here that one strangeness is coming, so there is S. One strangeness is coming, so there is S. And when there is two strangeness coming, so there are two S. So this way. Okay, I hope this question is clear to everyone. The other way you can, like, you can easily look into the option that which one is correct. So you know it very well that this is a baryon. You know it very well, this is a baryon, and strangeness is coming. These two, if I see these two options, so they are made up of quark and anti-quark, right? Again, they are made up of quark and anti-quark. And I already told you that mesons are made up of quark and anti-quark. But here, the strange particle is a baryon. So we are left with these two. Okay? We are left with these two, but we know that one strangeness is coming. So that means this one will be the answer. This is a short trick. I mean, when such questions are coming in the examination and they are of 1 marks, so just use this. Now I will move on to the fourth question. This again, I want you to at least do this question, because this is also a it's very easy question. I'll read the question. A particle Y undergoes strong decay. So this is the strong decay. This particle is some particle. This is pion negative plus pion negative. The isospin of pion, you need to find out the isospin of pion. I want all of you, at least I want all of you to do this question. I'll give you 1 minute time. This is again very easy question. So pions are pi positive, pi 0 and pi
I have
negative.
one.
What? 1.
One you just solved before. You just did this before
Ha, ha,
before slide.
ha. So it is 1, and iz will be -1, 0, and 1. So for pion negative, this will be 1 minus 1. Okay. So the isospin will be 1. So it is 1 and it is 1. So it is 2. So this should also have 2 isospin, right? And this is via strong decay. So now this is the table, and you can see in strong decay, isospin is conserved. So that means isospin should be conserved in a strong decay. So that's why the y is equals to 2 value. This also came in gate examination for 1 marks. These are the questions of 1 marks. Next time I'll try to
Ma'am,
solve.
please
Yes,
explain again why. How do you know that it will be two?
it will be 2 because this pion will give 1 and this pion will give 1. So 1 plus 1 add will give 2, right? So right hand side, the isospin value is 2. So left hand side should also have same value because this process is happening by strong decay. And I know that in strong decay, isospin should remain conserved. I mean isospin should remain. So that means left hand side should also have 2 as its value, like right hand side has. Okay. So this is a very important table. I mean, suppose such questions are coming. I'll give you one question, right? So if you can see here that in electromagnetic and weak interaction, isospin is not conserved. Okay. In electromagnetic, I'll repeat, in electromagnetic and weak interaction, isospin is not conserved. So they will give you such questions they will put question in such a way where right hand side isospin is not matching with left hand side isospin. And the if the process is going by strong interaction, you will say this process will not happen because isospin is not conserved. But if suppose the process is going on by electromagnetic or weak interaction and isospin is not conserved on both sides, then the process will proceed. It will depend on other quantities also. So this table is also very important. I mean, from exam point of view, this table is very important because in nuclear and particle physics, they will give you some random, so many means processes they will give you. They will give you so many reactions like these particles are combining and they are giving two other particles. So, will this reaction proceed? Will this reaction proceed by strong interaction? Will this reaction proceed by weak interaction? So, you need to find out each quantities like first charge, baryon number, isospin, Z component of isospin, strangeness. You need to find out in such a way so that at the end you can come up with a question that this reaction will proceed via this interaction. If suppose I am giving you any equation and I am telling you this reaction will go by which interaction, either it strong reaction, electromagnetic, or weak. So you need to calculate these quantities to come up with the answer that this will go by this interaction. Okay. I hope it is.
Ma'am, how do you know that uh,
Hmm.
this interaction always goes through strong interaction? How
I
do you know?
mean,
In this case,
actually,
you do not know the y particle.
yeah, I don't know the y particle, but in question it is given that it is going by strong decay. And I know this table because this table is this all this thing has been this always this all these quantities and how they are behaving with interaction, with which interactions. So they are all by scientists have discovered all these things, that this particular identical part, sorry, that this quantity will remain conserved in this interaction or in that interaction. So this is already proven. Okay. And in question it is given it is strong decay. So in strong decay, isospin should remain conserved. If it is not conserved, then you cannot say, you are not sure about it. So these are proven by scientists. those who have done discoveries, those who have spent their time in particle physics discovering different particles. So in particle physics, if you see, there are CP violation, there are everything. If you read this Particle Hunter or Griffith's book, you'll find so many things. So these are already proven, I mean, these things. Can we proceed to next question? Okay, this is the question from the last class. I did something wrong in it. The answer is same, but I did something wrong. I'll again explain it quickly. So this is the same way. Like this is the nitrogen. It has proton, number of proton 7, and neutron 7 minus 13 minus 7 is equals to 6. So this is what, this is even, so this won't contribute, and this is 7, so this will contribute. 1s 1 by 2, 1p 3 by 2, 1p 1 by 2. So here it will be 2, here it will be 4, it will be 1 here. So the ground state will be minus 1 raised to the power 1, that means minus. The ground state has negative parity. And okay, and this is going by first forbidden beta decay. This beta decay, first forbidden beta decay, second forbidden beta decay, this we have covered in the last class. So those who are new here, here they can see this is a question from the previous class. So the first forbidden beta decay we have done this in previous class. L is equals to 1. So delta I value will be 0 plus minus 1. These are the rules. These are the parity and angular momentum selection rules for first forbidden beta decay. And parity will change. So that means in these two, parity is not changing. So we are left with this. But again, as we have found out, in the ground state, the nitrogen has negative parity. So this question, this answer will be this option. So I have did something wrong in the last class, so that's why I have taken up this question in this class. Okay, moving on to the next question. This is gate 2020 question. I'll take a 1 minute pause. Now first I will read the question. According to the Fermi gas model of nucleus, this Fermi gas model of nucleus, the nucleons move in a spherical volume of radius this. This is the nuclei, and they are saying this nuclei is spherical in shape, and nucleons, neutron and protons are moving inside it. Hmm? The radius of it is given by r, and the value of r is also given, r naught a 1 by 3. R naught is a constant and A is a mass number. Okay. Now the Fermi energy of nucleus EF is proportional to, you need to find out the Fermi energy of nucleus this. First of all, let's just discuss this Fermi model of nucleus. Hmm? So what is this Fermi model of nucleus? It is a state of matter which is n group of many non-interacting fermion. Suppose this is a nuclei, and it contains so many nucleons, and we know that nucleons are neutron and proton, and they are fermions. So suppose they are lying in this constant potential and they are non-interacting particle, right? So they will follow a statistics which is known as Fermi-Dirac statistics. This statistic will help us to determine the energy distribution of these fermions, right? I'll again repeat, like it is a state of matter, you can say, in which there are non-interacting fermions, and these fermions are there in the potential, and this potential is due to the other fermions that are present there, and these fermions are non-interacting, and they will follow a statistic which is known as Fermi-Dirac statistic, and this statistic will help us to find out the energy distribution of these fermions. This is the case of 3D. So in 3D, we call it Fermi sphere. Means these fermions will form like a Fermi. This Fermi gas will form a Fermi sphere. Okay? And these fermions are neutron and proton, and they are moving inside a Fermi sphere. The radius of it is given r is equals to r naught a 1 by 3. You need to find out the Fermi energy. So this is the formula of Fermi energy. If this formula is from statistical mechanics, you know, in statistical mechanics we find out this formula for Fermi sphere, sorry, formula for energy distribution of fermions that are there inside the Fermi sphere. So this formula this is a straightforward forward formula. It is for 3 dimension. In 1D the formula is different. Now you can do this question. This is V, volume, and volume for a sphere is 4 upon 3 pi r cube, right? And this r is equals to r naught a 1 by 3. Put this in formula, you will get 4 pi by 3 r naught cube a. Now again put the value of v here, put the value of v here and solve it. Like this will go 9 pi and 4a, and this will come out r cube. This r cube will cancel this r, so f- Fermi energy will be inversely proportional to r naught square. So this is very straightforward formula, but the only thing, the key factor is this formula. Like this question was very straightforward, but this formula you need to you need to know, you should know this formula, and this formula is from statistical mechanics. If you have gone through statistical mechanics, you might be knowing this formula. So we are done with today class. If you have any doubt, you can ask me. Otherwise we will end this session, and you can give me feedback like for next class what all the topics that I can select.
Ma'am, if in a nucleus both neutron and proton are
Hmm.
odd
Hmm.
number, then which one will decide the total angular momentum?
Actually, it is a very nice question. Yeah, I'll tell you which one will decide. So there is a rule. Suppose if is there any space? Yeah. So neutron and proton, when neutron and proton both are even, then you know it's zero. Straightforward. When neutron is even, proton will decide. If proton is odd, when proton is even, neutron is odd, so neutron will decide. If both are odd, then this is very interesting. So this will have some j1 value, suppose and some l1 value, right? This will also have some j value and some l value. I'm denoting a neutron by j1, a neutron angular total angular momentum by j1, and orbital angular momentum by L1, and for proton J2 and L2. So what you need to do, you just add all these, J1 plus J2 plus L1 plus L2. Okay, if it is coming even, if it is coming even, so what will be the spin? Spin will be J1 minus J2. Okay. If it is coming odd, then this will be, oh sorry, not spin, J value, sorry. Then this will be J1 plus J2, and parity will be as usual. Parity will be minus 1 raised to the power L1 minus 1 raised to the power L2. We'll do this question like design question like this way. Suppose,
Ma'am,
okay,
what's this J1 and L1?
J1 and L1, yeah, I'm taking one question so that it will be, will get more clear understanding of this question. Suppose we have three, what is hydrogen, helium, lithium? Okay, so we have this lithium. We'll take it. No, seven will give how much? Seven minus three will give even. We'll take it six. We'll take it six. Okay, and then there is, yeah. So this is three, six, three. Six minus three is three. Okay, both are odd. That means n is also three, p is also three. Okay, so fill it. One s 1 by 2, 1p 3 by 2, right? So 1 s 1 by 2 will contain 2 neutron, and this will contain 1. Similarly, 1s 1 by 2 will contain 2 proton, and 1p 3 by 2 will contain 1. Now, for neutron, J1 value is how much? 3 by 2, because last neutron went to this subshell, right? And what is the L1 value? This is P. So what is the L1 value? 0, 1, right? Similarly, for proton, J1 value is, because last proton went to 3 by 2, and L2 value is how much? 1. Okay, add them. J1 plus J2, L1 plus L2. So 3 by 2 plus 3 by 2 plus 1 plus 1. How much? This is 6. No, this is 2, 3, 3, 2 plus 2. This is 6 plus 4 by 2. This is 10 by 2 is equals to 5. So this came out odd, right? So the total angular momentum value will be J1 plus J2. J1 was how much? 3 by 2. J2 was how much? 3 by 2. So that means 3 by 2 plus 3 by 2. How much? 3. And parity will be like 1 minus L1 minus 1 raised to the power L2. So minus 1 L1 is 1, minus 1 L2 is 1. So this will be minus 1 into minus 1 is equals to 1. So the answer will be 3 with parity positive. I hope it is clear. Hmm?
Yes, ma'am.
Okay. Then thank you everyone for joining the class. Okay. Now I'll end the meeting. Okay. Thank you everyone again.